Okay, be sure to put your name in chat, please. Can you hear me? Pretty certain you can see me. Can you hear? Come on, any more names in the chat than that? Okay. That's 6 people out of 18 in the room. And it's time. 15 seconds until time. And we started on logarithm functions last time. Yes, no, maybe so.
We were on section 5.3.
So we hadn't finished this. Have we done the exponential probability problem?
No, we stayed on the theorem.
Have we done this? The graphing?
No.
So we're all the way back here. About determining whether it's a, oh, I thought we'd done this already.
That's where we stayed. We stayed on determining whether they were exponential or not.
Oh, okay. So determining if they're exponential or not, it's about, is it going to be linear or exponential if we do we look at the average rate of change. If the average rate of change is constant, then it's linear. If the ratio of the consecutive outputs is constant, so you create a ratio with the current and the previous, with the current divided by the previous. And this is what we're looking at. The average rate of change is the slope formula between these 2 points, these 2 points, these 2 points, and these 2 points. If that is the same, then it's linear. And if it's linear, there's no way it's going to be an exponential, but they went ahead and checked anyway. So consecutive means here out comes 6 and 2. So it's 2 divided by 6, which is 1/3. And then the 2 and the -2. So it's -2 divided by 2, which is a -1. And then the -6 divided by the -2, which is a +3. And then the -10 divided by -6, which is a +5/3. None of these numbers are the same. So they're not constant. So it's not exponential, but it is rational. I mean, it is linear. This is the slope of the line. Linear means it's a line. And so this would be -4 times x. And where x is 0, that gives us our b value. So it's a -4x plus 2. Okay, and that's what they're talking about here. The slope is -4. The y-intercept is when the function, when x is 0, and so that was 2. And so here we have the function -4x plus 2. Now, in the second case, we look at the average rate of change. The first average rate of change is a -54, and then it's a -18, and then it's a -6, and then it's -2. Well, the average rate of change isn't the same each time. So that means it's not linear. And now we look at the ratios of the consecutive outputs. So the previous divided, the next divided by the former. So that's 1/3. So that's 27/81, which reduces to 1/3. And we go on down the line and we see that 9/27 is 1/3, 3/9 is 1/3, and 1/3 is 1/3. So they all equal the same ratio. So they're consecutive. So that means it is exponential, where the base is the 1/3. So when you do those, then you get the base, you get the ratio. That's the base of the exponential. So it's going to be 1/3 to the x. And the initial value is when x is 0. So the 27 here is the initial value. So when that's going to be 27 times 1/3 to the x power. So a is 1/3, which means we're going to raise 1/3 to the x power. All right. When x is 0, c is 27. So the c is 27, and so this is the exponential function. Now, in the third example they gave us, letter C, the average rate of changes were all different, 4, 3, 4, 5, 6. And the consecutive ratios were all different, and there's only one of them that reduced. And they're all different fractions, different ratios. So it is not, linear, and it is not exponential. So it's neither. Neither the average rate of changes nor the ratio of the two consecutive outputs is constant. So it's not a linear function because the average rate of change is a constant, and it's not an exponential function because the ratio of consecutive outputs is not a constant. So it's neither. Now they want you to graph this function. Well, it's putting numbers in for x, basically. And they put in, what is this? Nine numbers in for x. They put in a -10, a -3, a -2, a -1, 0, 1, 2, 3, and 10. And then they calculated what those are. All right. Actually, all we need to do is find out what these are and then do the reciprocal for the rest of them. The reciprocal of 3 is 1/3. The reciprocal of 9 is 1/9. The reciprocal of 27 is 1/27. the reciprocal of 59,049 is 1 over that number, which is decimal. And then you just start graphing. These get too small and these get too large. So we're basically looking at from -2 to +2 and possibly at 3, depending upon our graph, if we can do that here. Well, these numbers are just getting closer and closer to 0 because they get smaller and smaller fractions. So as x goes to the left, I'm going to get smaller and smaller fractions. And as x goes to the right, I'm going to get bigger and bigger numbers. So it's going to positive infinity that way. As x goes into infinity, the y values go into infinity. But as x goes to negative infinity, the y values get closer and closer to 0. The graph will have no x-intercepts because there's no way I can raise a positive number to an exponent and it will equal 0 or negative. So that means my range will be all positive real numbers and my domain is all real numbers. And so my x-axis becomes a horizontal asymptote. And the y-intercept is 1. Because anything to the 0 power is 1. So when I put 0 in for x, I get 1 for the y value. The table suggests that as x goes to a negative infinity, the f values approach 0. Therefore, the x-axis, y equals 0, is a horizontal asymptote of the graph as x goes to a negative infinity. So it's a horizontal asymptote for the left-hand side. On the right-hand side, yeah, it doesn't go down, but it's because it's always increasing. As x increases, y increases. We very often says it increases without bound. This provides in behavior for very large and negative. Okay, so as x gets very negative, then we have a horizontal asymptote. And as x gets bigger and bigger, what happens to f of x? Well, f of x gets bigger and bigger. As x gets bigger, the y values get very huge very quickly. If I multiply 10 to the 3rd by 3, which is 10 to the 11th, I'm multiplying this by 3, which goes close to 180,000. So I'm multiplying each number by 3, 9, 27, 81, 243, 72, 9. I don't know what the next one is. 729, and then the next one is 2100. Okay. So as x grows, f of x grows very quickly. It increases in value very fast. So that's, yeah, it has exponential growth, means it's growing very fast. Bacterial growth and viral growth are exponential. Using this information, plotting some points and a table and connecting with a smooth and continuous curve, this is what the graph of x to the third, 3 to the x equals. This is what it looks like. All right, here they have the horizontal asymptote. They go ahead and continue it in both directions. All the y values are above 0, and all the x values are the real numbers. So you can have negative x values, you can have positive x values, you can have x equal to 0, but all your y values have to be a positive number. And from the graph, you can see that the range is all positive real numbers. And the function is increasing. If you look at it, you can see that it is increasing over its entire domain. And if you go way far to the left, it comes up from 0. It never equals 0, so it's a very small fraction close to 0 and starts getting bigger and bigger until it starts exploding upwards once you pass, once you get into the positive numbers. And so it's always increasing, so that means it's 1 to 1, which means it has an inverse function, which are the logarithm functions. X3 is the inverse for this. The domain is set all real numbers. The range is all positive real numbers. There's no x-intercepts, but the y-intercept is 1. The x-axis is a horizontal asymptote as x goes to negative infinity. When a is greater than 1, it is an increasing function, and it is 1 to 1 and has an inverse. The graph of the function contains those 3 points. -1, 1 over a, because a to the -1 is 1 over a. 0, 1, because a to the 0 equals 1. And 1a, because a to the first power is 1. The graph is smooth and continuous with no corners or gaps. And we'll look at the function on the next page, on the next slide. I'm looking for my black pen. I hid it on myself. Yes, I did. I put it in my pocket. Now, the title of this is talking about the exponential f of x equals a to the x, where a is greater than 1. So from f of x, this is on is f of x equals a to the x, where a is greater than 0. I mean, a is greater than 1. Okay, and the graph will look something like this. All exponential functions where a is a number, a real number greater than 1, will have this shape, or some some of them come up like this and grow faster, and some come in like this and grow slower. So the closer to 1 you get, the flatter the curve is, but it never goes totally flat. And the further away from 1 you get for A, the steeper this curve is, and the quicker it comes down towards the x-axis. Okay, so just need you to be aware of that. But they all follow this general shape. So now to graph, well, there's a couple of ways of looking at this. Because I know 1 over 3 is 3 to the negative 1, so I could say 1 over 3 raised to the x power is 3 to the negative 1 to the x power, or 3 to the negative x. So I can do a transformation on the 3 to the x function. Or I could do this. I do a table. And I use the same values for x that we used on 3 to the x. And please notice here, when they wrote this here, they said it was 3 to the 10th power. This is 3 to the 3rd power. This is 3 squared. This is 3 to the 1st. This is just 1. And then this is just 1/3 and 1/3 squared, 1/3 to the 3rd, and 1/3 to the 10th power. Which this is 3 to the negative 1, 3 to the negative 2, 3 to the negative 3, 3 to the negative 10, which if you take from the other, if you look back at the table for x to the 3 to the x power, these values over here we got for f of x have been flip-flopped. Because we're doing the reciprocal of what that was, because 1/3 is the reciprocal of 3. That doesn't say that they're inverse functions, it says that they're reciprocal functions. Inverse functions and reciprocal functions are different things. So now we start graphing these. Locate some points on the graph as shown in the table. So if you notice, again, all our y values are going to be greater than 0. So that means our range will be y greater than 0. The graph lies above the x-axis and has no x-intercepts, and the y-intercept is 1, just like f of x. 3 to the x did. As x goes to infinity, to negative infinity, the function grows very quickly, all right? So as x gets more and more negative, the y values get very, very large. And as x goes more positive, the y values get very, very small. Get small. So now, it kind of flip-flopped what happened with 3 to the x. Now, when x goes to negative infinity, the y values get very large. And now when x goes to positive infinity, the y values get very small. They approach 0. The larger x gets, the closer to 0 you are. So that just like 3 to the x, you have a horizontal asymptote at the x-axis, y equals 0. As x goes to positive infinity. The function is decreasing. And it is a decreasing function over its entire domain, which means it's a one-to-one function. And so it has an inverse, which is the logarithm. So 3 to the x took us like this. Where this point is actually over here, and this point is over here, and this point is over here, and this one is over here. Where I'm changing the sign on my axis. So this is f of x equals 3 to the x, where this one is this function. All right, so the domain hasn't changed. The domain is all real numbers. There are no x-intercepts. Oh, and the range is all positive real numbers. So it's like with when a is greater than 1. So this here, the restriction is now that a is a fraction between 0 and 1. So the domain is still all real numbers, and the range is still all positive real numbers. There's no x-intercepts, and the y-intercept is at 1. The x-axis is the horizontal asymptote as x goes to positive infinity. When the base is a fraction between 0 and 1, it is a decreasing function, and it is one-to-one, which means it has an inverse. Again, these 3 points are contained on that graph. -1, 1 over 8. Right? A to the -1 is 1 over 8. So you get the reciprocal of a. Anything raised to the 0 power is 1. And anything to the first power is that thing raised to the first power. The graph is smooth and continuous with no corners and gaps, and boom, there it is. It's a reflection of if a was greater than 1. So if you have the reciprocal of a, then they're going to be reflected across the y-axis, where this point would be over here, and this point would be over here, and so it would go up like that, and it'd be symmetric across this. So They have reciprocals of each other. And they also have inverses of each other. So to graph this, okay, so we start, I'm trying to figure out what they start with. Do they start with the +1 or do they start with the negative of x? So let's see. Here's x to the third. I mean, 3 to the x. I'm thinking they're going to do the negative x. Did they do the negative x? Yes, they did the negative x. That means the negative 0 stays 0, but the 1 of 1, 3, the 1 becomes negative. The negative 1, 1/3, the negative 1 becomes positive, so it's 1, 1/3. And the negative 2, 1/9 becomes 2, 1/9. Right, so that's what they have here, these points here. And then they're going to add 1 to the y values, right? Remember, if you're changing it after the parent function, then it's going to be a change in the vertical direction. So I'm going to add 1 to each y value here. So this goes -1, 4. This goes 0, 2. This goes to 1 4/3. And this goes to 2 and 1 1/9. And this is 1 1/3. So, yeah. So 4/3 and 10/9. So adding 1 to each of these y values gives you these points, and then the graph, and adding 1 to the y to the horizontal asymptote. So adding 1 to y = 0 gives you y = 1, and so there's my new horizontal asymptote. Your asymptote changes right along with the rest of the function. It's just the change in the x values doesn't affect the horizontal asymptote. It would change a vertical asymptote, but not a horizontal. But a change in the y value changes your horizontal asymptote. Because everything, in this case, everything got shifted up. So the domain remains the same because it doesn't matter what I put in for x, I can still use it. But what changes is the numbers I get. Now the smallest number I get is greater than 1, and it goes up to infinity. So, and then the y-intercept went from 0, 1 to 0, 2. So the y-intercept is 0, 2. The horizontal asymptote is y = 1. The range is from +1 to infinity. Okay. Oops. Any questions here on this? All right. E is defined as a number in the expression 1 + 1/n⁻⁴. As n approaches infinity in calculus, we use the limit notation. The limit as n goes to infinity of 1 + 1/n⁻⁴. So what this is saying is, as n gets bigger and bigger and bigger, what does this fraction or what does this expression come to? What number does it approach? And it approaches a number we call E. which is 2.7 something. It's an irrational number. We call it E because of the man who discovered it. His name was Euler. Euler. Some French dude living in France back in the 1800s or the 1700s, I think the 1800s, like 1700s. His name is Euler. I don't know, it's French. I don't know why. I always thought in French ER was pronounced as A, but Euler was he was quite prolific and a very important mathematician. He did a lot of work with pathways and nodes. If you're in computer software design, everything you do there is built on, in part, built off of his work dealing with pathways. He lived in Paris, and I think there were 7 bridges that crossed the River Seine, or whatever it's called, the river that goes through Paris. And he looked at, can you cross those bridges in such a pattern without ever crossing your own path and still coming back and still being able to come back to the spot you started from? And so that's the kind of work, a little bit of the work he did stems off of that. And so defining pathways, how do you find pathways, how do you build nodes, and that sort of thing. Okay. So E is an important concept. It's an important number. We see it all the time. It's used, E to the X is used in engineering quite extensively. It's used in all kinds of engineering. It's used in mathematics and in physics. Population growth, so it's used in the social sciences. E to the X, E to the first, here they rounded it to 2.72. It's 2.718, and that's all I remember. I used to know what the next 2 decimal places were, but I don't think it's necessary to remember them. It's like pi. You don't always need to remember them because you got pi on your calculator. It's a useful irrational number, just like pi is a useful irrational number. And this is the graph of e to the pi. E to the x. E to the -1 is negative. It gives you the point -1 over e. E to the 0 gives you 1. E to the first power gives you e. So these 3 points squared, or 1 over e, or 1 over e squared. But when graphing, you want to put it in the calculator so you can approximate where it belongs. All right. So to graph this thing, we start with e to the x. And then we throw the negative sign at it. When we throw the negative sign at it, that means all our y values become negative now. So this becomes a negative 1 over e squared. This becomes a negative 1 over e. And this becomes a negative 1. This becomes negative e. This becomes negative e squared. And so instead of being above the y-axis, x-axis, now it's below the x-axis because all our y values went negative. That's the only way you get a negative number with exponentials is that if you multiply it by a negative number, or multiplying by a negative. Now, in the exponent, we're going to add 2 up here. Is it plus 2? Yeah, plus 2. So when you adding 2, that means you have a horizontal shift 2 units to the left. So that means each of these x values go 2 units to the left. So this negative 2 becomes a negative 4. This negative 1 becomes a negative 3. This 0 becomes a negative 2. This 1 becomes a negative 1. And this 2 becomes 0. And that's what we have here. I meant to resize this so it's closer to that. Any questions here? From the graph, you can tell that the domain didn't change. I can still put any number for x in there. But what changed was my range. Instead of being all positive real numbers, now it's all negative real numbers because I'm multiplying by that negative sign. The horizontal asymptote remained y equals 0 because I didn't do a vertical shift. And the x-intercept went from being down here at 1 or negative 1, now it's down here at negative e squared. Because we shifted everything 2 units to the right, to the left. Now here's a this is a new property that we really haven't discussed before. That it should, just on the face value, it makes perfect sense. If the bases are the same, then the exponents have to be equal. Because that's the only way they could be equal, is if the exponents equaled each other. Now the 2 exponents could be different expressions, but as long as the base is the same, then that means the exponents have to be equal. So like on this. Now, I can write 8 as 2 to the 3rd power. So this equation I can write as 2 to the x plus 2 equals 2 to the 3rd. Well, for these 2 expressions to be equal means the exponents have to equal. Because x plus 2 equal to 3 means x has to be 1. Because 1 plus 2 is 3, and 2 to the 3rd power is 2 to the 3rd power. Now, in letter B, it's not as easy. I do have to change to the same base. So now here I have 9, as a base, and here I have 27 as a base. Well, I know 9 is 3 squared, and 27 is a perfect cube, 3 squared, 3 cubed. So I can rewrite the 9, oh, the solution set this one. I can write the 9 as 2 squared, 3 squared, sorry, raised to the 2x minus 5. And I can write 27 as 3 being squared, raised to the x. And I use the property of raising a base to a base. Raising a power to a power, you multiply the exponents. So this becomes 3 to the 2 times 2x minus 5. And this becomes 3 raised to the 2x. And since the bases are the same, then that means the exponents have to equal. So 2 times that should have been a 3 here. Sorry. Two times 2x minus 5 is going to equal 3x. And then I just solve for x. I use the distributive property to get rid of the parentheses. So I have 4x minus 10 equals 3x. I subtract 3x from both sides and I add 10 to both sides. So 4x minus 3 is 3x is x, and I add 10 and I add 10. So x equals 10. And that's my solution set. Sorry, and they do the same thing. And they get the same solution, which they should. Unless someone really screwed up. Now this one's going to look a little trickier, but we're going to rewrite the right-hand side so it's e to some power, not two different e's to some powers. So we rewrite 1 over e to the negative to the 6th power. We can write that as e to the negative 6. So I want to bring this out of the denominator so I can multiply like bases together. So to do that, I have to change my exponent on e to be negative. So then I can pull it out of there. Right? That's using the fact that a to a negative s equals 1 over a to the s. Well, I can go back the other way. Remember, I said we were going to be using these properties a lot. Now, when I'm multiplying like bases, I combine my exponents. So this becomes e to the x minus 6. Now, e to the negative x squared is going to equal e to the 5x minus 6. So that means negative x squared and 5x minus 6 are going to equal each other. Right? Because if the bases are the same, then the exponents are the same. And then we just solve for x. Well, I'm going to bring that x squared over to the same side as the 5x minus 6. So I get, and here's where some issues happen. Let me back up 1 second. I typically do it this way. I typically add the x squared because I want my x squared to be positive. So I'm going to, because it makes solving the problem easier. So now I have 0 equals x squared plus 5x minus 6. There's no like terms to combine, so we write it as an expression. Now, the issue is people aren't used to this. 0 equals. Well, it doesn't matter. The symmetric property of equality, A equals B, also means B equals A. So it doesn't matter which side the equals 0 is on. So I can rewrite it this way and just ignore this over here. It means the same thing, that this is the expression of 0. So, and that's what they do. They write it this way. I would leave it this way and then just solve it the same way. It doesn't matter which side that equals 0 is on. It's like 8 equals 5 plus 3 is the same thing as 5 plus 3 equals 8. Doesn't matter which side the equals 8 is on. They're equal. Okay, getting off my high horse now. So I can factor this. This should look familiar. Leading coefficient is 1, so it's going to be an x and an x. The factors of 6 that subtract to 5, well, that's 6 and 1. 6 minus 1 is a positive 5, so that's the signs. Plus 6 minus 1. Set each factor equal to 0. Right? Using the 0 product rule. X plus 6 equals 0. Subtract 6 from both sides, you get x equals negative 6. X minus 1 equals 0. Add 1 to both sides, and you get x equals 1. There are my solutions, negative 1 and 1. If you want to check that they work, then do them one at a time. Put negative 6 in for x. Do you get the same thing on each side? Put 1 in for x. Do you get the same thing on both sides? Okay. This problem is kind of fun. I don't know. I think it is. There's some typos in this problem, but they're not very severe. They're just annoying. I put a 9 in when I should have just dropped it. Drop it already. Okay. So here we have between 9 and 10 p.m. Cars arriving at this particular Burger King's drive-through at a rate of 15 cars per hour. So during that hour, they anticipate 15 cars to show. Not necessarily all at once, but who knows? Okay, so that rate is the same as 0.25 cars per minute. So a fourth of a car every minute. How does a fourth of a car show? Well, this is called a unit rate per 1 minute. This is a unit rate per 1 hour. When it's per a single unit of measure, then it's a unit rate. At HEB, if you look at the price tab, they usually have a unit rate. How much money per ounce, or how much money per pound, or how much money per individual item. So you might have a pound of spaghetti and its unit rate is per ounce. And so that's where you start comparing unit rates. For a long time there, I used to tell, but this is back when I was in Pearson. And even until I think when I got to Poteet, I quit doing this. If you know you have a 1 pound package of spaghetti and a 3 pound package of spaghetti, and people are used to being the larger package costs less. So if you bought 3 pounds of the individual 1 pounds, it's going to be more expensive than a package of the 3 pound. Well, I took a quick look at the unit pricing, and it was cheaper to buy 3 1 pound packages than it was to buy the 1 3 pound package. So looking at the unit price is a good way to save money. You're feeding a large family, yeah, every penny you can save is a good thing. Okay, so that's unit rates. The following formula from statistics can be used to determine the probability that a car will arrive within 10 minutes, T number of minutes of 9 p.m. So letter A, if T is 5, so within 5 minutes of 9 p.m., that means before 9:05. So this is the number of minutes, T, the number of minutes after 9. So what's the probability that one car will show up within those 5 minutes of time? What's the probability that one car will show up within 30 minutes? So like between 9 and 9:30, what's the probability that you'll have one car show up? At least one car show up. You can have more than one show up, but we're just looking for the first one. So since this formula T is in minutes, and this is 5 minutes, so I just put 5 in for T and see what that equals. And then I put 30 in for T and see what that equals. And then we look at the graph. And then we look at what happens to the graph as T gets very large. So putting 5 in for T. Well, that's just putting this into the calculator. Ignore this 9. It's not supposed, see, because here they're rounding this 4 to a 5, so they can just forget about this stuff down here. But they put that 9, someone with a twitchy finger put a 9 in there. Okay. So 1 minus e to the negative 1.25, which is this number. And so probability, this is a probability, is between 0 and 1. And as a percentage, it's between 0 and 100. So changing this to a percentage, it's 71.35%. So we have a probability of 71.35% that a car will arrive within the first 5 minutes of the 9 o'clock hour. So now we want to find out when T is 30 minutes. So what's the probability that a car will show up within the first half hour of 9 o'clock, the 9 o'clock hour? So you put 3:30 in place of 5 here. You replace the T with a 30. So this is going to be e to the negative what? 7.5, I think. 3 times. Yeah, that's going to be a negative 7.5. So e to the negative 7.5, and it's 1 minus that. Well, that's this lovely number. And so we round to 4 decimal places. The 4 here tells me we stay at 4, so we have this. And to write this as a percentage, decimal goes between those 2 nines. So it's 99.94% that a car will arrive within 30 minutes of 9 o'clock. So that's not quite 100%, but you're pretty much guaranteed a car in that first half hour. Or maybe everybody's going to, maybe all 15 cars are going to show up within the last 5 minutes of that hour. You never know. But this is on average. This is on average. Okay, probability is not certainty. Now the graph, you just plug it into the graph, and so from 0 to 30. So at 5 minutes, we were at this point here, and at 30 minutes, we're so close to 1, it is almost 100%, but it isn't. But what's going to happen to this curve as we're talking about more and more minutes? What happens to that curve? What value is it approaching? Well, the larger t gets, the closer to 1 the function gets. Because if you look at the denominator, if you look at that e to the negative what was the formula again? I forgot. Oh, negative 2.5t, as t gets larger and larger, this number here gets smaller and smaller because of the negative exponent. It's 1 over, right? It's 1 over e. So as t gets larger, this number down here gets larger, but the fraction gets smaller and it approaches 0 as t approaches infinity. So as t approaches infinity, this approaches 0, so the function approaches 1. Because this will drop away and you just have 1. But can t go to infinity? Because we're just talking, we have a limited domain between 9 and 10. So t is between 0 and 60. So beyond 60, we don't talk about because that's not between the hours of 9 and 10. But anyway. The algebraic analysis is supported by the figure on the previous slide, which is this thing. So if you set your range out to 100, it'll y equals 1 in this graph will look like the same line. For all intents and purposes, they are the same line after a certain point. Simply because the difference between the two is so minuscule, it's hardly hard to see. Okay. Logarithm function. So with this, we're gonna look at what makes a logarithm function, and we use an exponential function to define the logarithmic function. And so we're going to be able to change from a exponential to a logarithmic and a logarithmic to an exponential. Because they're inverse functions of each other, there are quick and easy ways to rewrite them. Logarithms are exponents. You will hear me say that till you want me to shut up, like you want me to do right now. Okay. And then we're going to evaluate logarithm expressions. We're going to be able to determine the domain. We're going to look at the graph, and then we're going to solve logarithmic equations. And sometimes that involves using its inverse, which is the exponential. Okay. Here's a definition of logarithm function. A logarithmic function is defined by its exponential function. So y equals the log base a of x. That's how this is read. Y equals the log base a of x. All right. It is not written log a x. No, this is a subscript. This is a subscript. So you need to make sure that you are very clear what the base is. So I could say the log base 9 of 8. What does that equal? Well, that equals x. Or actually, they're saying y here. So what this means is logarithm is an exponent. The logarithm equals the exponent we put on the base that equals the argument of the logarithm. So that would be 9 to the y equals 8. These two statements are what we call equivalent. They're equivalent statements because y is the same value in each of these, in both of them. Okay. Y equals log base x means, what it means is that y is the exponent you put on a to equal x. The logarithm equals the exponent we put on the base to equal the argument of the logarithm. Y is the exponent we put on a to equal the argument x. The domain is all positive real numbers. You can only take log of a positive real number. A has to be a real number greater than 0, and it can't equal 1. Familiar? Isn't that the restriction on A for the exponentials? Yeah, since they're inverses, they need a similar restrictions. Otherwise, it doesn't work. Since logarithms and exponentials are inverses, the range of an exponential is positive real numbers, so that makes the domain of logarithm functions positive real numbers. And since the domain of the exponential is all real numbers, then the range of logarithm will be all real numbers. So your domain and range flip-flop. Y is the exponent we put on the base 7 to equal the argument x. So x equals 7 to the y power. So 2 will equal log base 7 of 49, which means 7 raised to the exponent will equal the argument. 7 to the second power equals 49. Y is the exponent I put on the base to equal the argument of the logarithm. So 4 to the y will equal x. And it goes the other way as well, right? So -1 is the exponent I put on 4 to equal the argument of 1/4. So 4 to the -1 is 1/4, which we know is true, so that makes that true. Now to go the other way, 3 is the exponent. So 3 will equal the log base 1.6 of w. What the exponential equals is what is the argument of the logarithm. So 0.16 is the base, and the log equals the exponent, and what the exponential equals is the argument of the logarithm. Same thing with letter B, e to the u. The u is the exponent that equals the log base e of 25. So the 25 is the argument of the log, e is the base of the log, and the u is what the log equals, because the u is the exponent. B to the 5th equals 27. So the base is b, and what the logarithm will equal is 5. So the log base b will equal 5, and the 27 that the exponential equals is the argument of the logarithm. You're switching your x and your y, and your base remains the base. Three is the exponent I put on b to equal 8. 3 is the exponent I put on the base to equal the argument. -2 is the exponent I put on the base to equal the argument. So e to the -2 will equal c. Same thing here. 4 to the w will equal 6. 4 is the base, w is the exponent, b is what the exponential equals. Argument 6 is what the exponent is what the exponential equals. You will have a total of 6 problems on the next exam that deals with these types of conversions. 1 is from logarithm to the exponential, and 3 of them from the exponential to the logarithm. I see these as easy problems. You're going to have 6 of them. That's 60 points. Please know how to do this, because you can't afford to lose those 60 points. That's why I put 6 of them on there, because I think this is 60 easy points. And what I take points off for on that is, did you put the numbers in the right spots? So you have 3 things to worry about. 1, 2, 3. 1, 2, 3. So I take off points if you put them in the wrong spaces. So if you put the H here and the 3 here, then that's a -6 points out of the 10. You had the base right, but you had the other 2 numbers wrong. If I switch these 2, that's a -6. Because the base is B, not 3. 3 is the exponent. And here's a very important thing. I need y'all to remember this from now until you're done with this class. When you're asked to change from a logarithm to an exponent, it doesn't mean you find out what the variable is. It just means you rewrite it as an exponential, or you write the exponential as a logarithm. I'm not trying to find out that b is 2. I'm not going to plug e to the -2 into the calculator to find out what c is. No, I want this. When you're asked to rewrite as an exponential, or rewrite a logarithm as an exponential, or rewrite an exponential as a logarithmic, I need the expression. I need the equation. I don't need to find out what the variable is. I don't need you to verify that it does equal. Okay. That's important, because can't tell you how many people in the past have done that. They go, oh, well, then that means b is 3, so that's my answer. B is 3. As long as you have this here, I will accept that as the answer, and I'll just kind of X that out and say, no, this is what I was asking for. Because that's taking too much energy and put too much time into it. But you have other problems that are more complicated. So finding the exact value, well, and they're going to use y, so I'll use y. This equals y. I'm going to find out what that equals. Well, I'm going to rewrite this as an exponential, because 3 to the y power equals 81. Well, I know 81 is 3 to the 4th power, so that means y equals 4, right? If the base is the same, then the exponents are equal. So that means this equals 4. This is a case where you're trying to find out what it equals. Same thing over here. All right, so that means 5 to is going to equal y. So 5 to the y power is going to equal 1 over 125. Well, 125 is 5 to the third power. Remember the first 6 perfect the first 6 perfect cubes. That's one of them. But I don't want 5 in the denominator. I need it in the numerator. So that means my exponent is going to become negative. So both are in base 5. So that means the exponents are going to equal. So y equals a -3. So this equals a -3. And that's exactly how they do this. Think 3 ways to what power equals 81. So there we have it. And they do letter B the same way I did. So 5 to some power equals 1 over 125, or 1/125. And so they did the work over here. 125 is 5 to the third, and so to bring that out of the denominator, so they're both on top, then it's 5 to the -3. And so setting the exponents equal, so that means the log base 5, 1 over 125 equals -3, which is what I got there. Questions here? Knowing your first 16 perfect squares, knowing the first 6 perfect cubes, and knowing the first 4 to the 4th power, 1, 2, 3, 4 to the 4th power, come in extremely handy here. Knowing that 625 is 5 to the 4th power is extremely helpful because that shows up a lot. 25 squared is the same as 5 to the 4th power. So that comes in handy. The domain of logarithmic functions is the range of the exponential function, which is from 0 to infinity. The range of a logarithmic function is the domain of an exponential function, which is all real numbers. So the domain is all positive real numbers, and the range is all real numbers. So y equals log base a of x if and only if x equals a to the y. The if and only if means it goes both ways. It means if you know this is true, you know this is true, then this is true. And if you know this is true, then this is true. Because they're inverse functions. And so that will hold up no matter what the base is. Now the domain, what you can, logarithmic functions what you can put into a logarithmic function has to be a positive number. Because non-positive numbers do not exist in logarithm. You can put it in there, but in your calculator, it'll say, "Oop, I don't know what you're telling me, but it can't happen." Okay. So that means x plus 2 has to be greater than 0. Since the absolute value of x, I'm going to look at C first and then look at B. Since this is greater than or equal to 0, the absolute value gives you a positive number or 0. So that means I need to exclude 0 because I can't use 0 in logarithm. So in this case, this is easy. X isn't 0. All real numbers except for 0. And this is setting x plus 2 greater than 0. So x has to be greater than -2 by subtracting 2 from both sides of the inequality. Okay. And that's what they did here. They subtracted 2 from both sides and got x greater than -2. So x is any real number from -2 to infinity, open at both ends, which means it won't equal -2. Now, letter B, that fraction has to be greater than 0, which means both the numerator and the denominator have to be greater than 0. So 5 plus x has to be greater than 0, and 5 minus x has to be greater than 0. So in the first case, you're going to get x is greater than -5. And in the second case, you're going to get 5 is greater than x. So x is kind of between -5 and not kind of, it is. Because if I rewrite this one so the -5 is first, so -5 is less than x, and I switch this one around so the 5 is second, so now x is less than 5, so it has to meet both of these criteria, so x has to be greater than -5 but less than 5. So -5 is less than x is less than 5, which is the interval from -5 to 5. So as long as x is in that interval, not including the endpoints, as long as x is in that interval, you'll get a positive number there, so the domain is all real numbers between -5 and 5, exclusively. So we have two ways of representing this, and that's using the inequality, or the interval notation. Either way. Okay. Yeah. Oh, and letter C. I didn't do this at the top there. The absolute value has to be greater than 0 for us to use it in the logarithm. So that means x can't be 0. So you can use the phrase all real numbers except 0, or you could say x not equal to 0. All x such that x is not equal to 0, or you can use that where you have two intervals, one below 0 and the other above 0. And so, and it's the union of those two sets of numbers. Now, the properties here of logarithms is very similar to the properties of their exponential. Oops, forgot to erase that as well. Right? The domain is a set of all positive real numbers. The range is a set of all real numbers, which is just the flip-flop of the domain and range from the exponentials. And again, there's, and then the x-intercept is 1. So here we have an x-intercept, but no y-intercept. So that kind of flip-flopped as well. Because with the exponentials, the y-intercept was 1, and there was no x-intercept. But now, the x-intercept is 1, and there's no y-intercept. The y-axis, x equals 0, is a vertical asymptote, where with the exponential, the y-axis, no, the x-axis was a horizontal asymptote. The function is decreasing when the base is a fraction between 0 and 1, just like with the exponential. And it's increasing when a is greater than 1. When the base is greater than 1, then it's going to be an increasing function. And it's going to be 1 to 1, just like the exponential. So this property is the same in both logarithm and exponentials. The graph contains these 3 points, which if you remember from the exponentials, we just switched the x's and y's. With the exponential, it's 0, 1, but with the logarithm, it's 1, 0. With the exponential, it was 1a, but with exponentials, with logarithms, a gives us 1. And same thing here, it's the reverse. The graph is smooth and continuous with no corners or gaps. And so this is what we have. 2 sets of graphs here. One for when a is a positive fraction less than 1. And the red is the logarithm and the blue is the exponential. Notice they intersect on the line y equals 1. And we're just switching 1, 0, 0, 1, 1 over a, negative 1, negative 1, 1 over a, 1a, a1. Same thing over here, do the exact same thing, except now both of them are increasing, where this is the exponential and this is the logarithmic. The exponential grows faster than the logarithmic. And this is when A is a number, a real number greater than 1, the base. So these two functions are reciprocals of each other, just like these two functions are reciprocals. I mean, are inverses of each other, not reciprocals. These are inverses. Reciprocals are something different. Now, natural log is base E. I know this looks like a 1. It is not a 1. It's an L. Right? This is not a 1. This is what a 1 looks like. This is an L. I wish they used a different font here. Textbooks are notorious. It looks like 1N, but it isn't. It's LN. So I usually use script, cursive, LN. Natural log of X. All this means is log base E. Natural log is a common log. It's a log we use a lot. So instead of writing log base E all the time, they decided to shorten it by just using LN for natural logarithm. The N is natural, the L is logarithm, natural logarithm. And it follows all the same properties. Its inverse function is y equals e to the x. The base is e, the base is e. It follows all the same rules. It's just a specific case of logarithms. When I taught calculus in high school, I had students who thought when I wrote natural log, they thought I was writing 1N. Okay. Let's see what the next slide is. All right, we'll start with this slide next time. I'm going to quit now. I'm operating on about 2 hours of sleep from last night. I was grading all the exams for this class. I'm done grading them. I just haven't done the magic on them. The grades were pretty pathetic because very few people showed their work. I told you to show your work. Very few people did. There was at least one person who would have made at least a B on the test who didn't do well at all because they didn't show any work. You have to show your work. I can't grade it. If you don't show your work, I can only give you, if you got the correct answer, I can only give you 2 points out of 10. I told you that. So please show all your work. I'm super tired and a little frustrated. I'm sorry, I didn't mean to fuss at y'all like that. What I'm going to end up posting is the raw scores, and I'll do some adjustments later on. I will be posting, I have to do it each exam one by one, but I'm going to put back, I did all the grading already on my paper tablet. And I have to re-upload that into my computer so I can re-upload that into the assignments exam too. And so you can see my notes and stuff. Yeah. And geez. Oh, and we'll have to talk about how you post things. Some people only didn't post everything. It's only got part of the exam from some people. That was one thing that happened. And another thing that happened, instead of getting something this big, I got something about this big. So I couldn't read it very well. I was able to read it and I was able to grade it, but it was hard. And please double check to make sure it comes across as a paper-sized document, PDF. I don't know what happened. It was just one person. I don't know what happened with that. It was probably the program that was being used. I'm done with y'all. So you're quite welcome to leave if you need to. If you have questions for me, I'll be here for a little bit. But got something going on. So if you got a question for me, now's the time to ask.
Bye, sir. Have a good day.
You too. Okay. I'm shutting things down.